Hi, I'm Dr. Eva Horvath, and this is part of the BocaPhysics series on electromagnetism. In today's video, I'm going to be discussing electrostatic boundary value problems. In particular, I'm going to be giving the justification for solving Laplace's equation. Up till now, we've been solving for the electrostatic potential or the electric field, as the case may have been, using an integral expression. The potential is given by 1 over 4 pi epsilon naught times the volume integral of the volume charge density divided by the magnitude of the separation vector. Remember, as always, prime coordinates correspond to source points in space. Unprime coordinates correspond to field point or observation points. So we are integrating over the source points here. So another way of solving electrostatics problems is to use a differential equation. And we're going to be using Laplace's equation, which we derived in a previous lecture. It's instructive to look at this before we get into all the nitty-gritty of solving this for electrostatic boundary value problems, to look at the behavior of this equation in 1 dimensions and also 3 dimensions. We'll kind of skip over 2 dimensions here. But anyway, in 1 dimension, we've only got 1 variable to deal with, and we might as well choose x. And since it is just 1 dimensions, our partial differential equation becomes an ordinary one. If I solve for that, you can write an answer down immediately. The potential is just equal to ax plus b, where a and b are constants. I haven't completely solved it yet because I don't know what a and b are. Those are just integration constants that came in when I solved this expression. Once we've discussed the uniqueness theorem, we can say, well, how can we solve for a and b? For the time being, though, I just want you to focus on the form of this equation, and let's plot it. Or I should say plot what it might look like. We might have a line given by going from here up to here, or who knows, maybe we have a line looking like that. We don't know a and b yet, so who knows which way our line is drawn. But the one thing we do notice about either of these graphs is that the extrema occur on the boundaries. There's no extreme in the middle. It's not like you go like that. It's just a straight line. That's a feature of all solutions of Laplace's equation, regardless of whether you're talking about 1 dimension, 2 dimension, or 3 dimension. So, important note. The extrema occur on the boundaries, as you can clearly see from either of these 2 lines that I've drawn. Number 2, Laplace's equation is kind of an averaging process. And 3, solutions of Laplace's equation are hot lots. It seems like a pretty easy answer there. However, once you get into 2 and 3 dimensions, you'll see that your answers can get very complicated very quickly. So I'm just going to say a few words about 2-dimensional cases first. Now we'll choose our two coordinates to be x and y, so therefore Laplace's equation becomes second partial derivative v with respect to x plus the second partial derivative v with respect to y. We're going to solve this expression in Cartesian coordinates, but we'll also encounter problems in spherical coordinates and in cylindrical coordinates as well. There is another method, one that we're not going to get into in this course, for solving Laplace's equation, and specifically for solving two-dimensional case. It's using complex analysis. If you ever take a class on complex analysis, you may have talked about a method called conformal mapping. It's usually not used very much anymore. It seems like it was in much wider use back in the day, back in the 1940s or 50s. And basically, the idea behind it is that you want to map your problem over to the complex plane, and then you want to map your problem in the region you want to solve for into another complex plane where the problem's easier to solve. You map your solution back into the original complex plane, and there you have your answer. It's a powerful technique. It's limited in the types of problems that you can handle. I found it to be kind of interesting. Gives you some insight into electrostatics that you may not have seen otherwise. But as I said, it's graduate level, so we won't be getting into it in here. But it's just FYI. So sometimes you can use conformal mapping, but for the most part, we will be using separation of variables to solve this expression. Okay, so let's talk about three dimensions. Not surprisingly, we wind up with one third term here that is the second partial derivative of with respect to z is equal to 0. So we have this vanishes. I'm going to delve into this whole averaging business a little bit more. And I'm going to assert here that the potential at some point r is equal to the potential averaged over a sphere centered at that point r. Again, I want to make this problem as easy as possible to solve for myself. So why not center my sphere at the origin? And I'll stick my charge Q some distance on our way. But since we get symmetry in this problem, why not evaluate it along the z-axis? So therefore my average potential is going to be divided by the surface area of the sphere. So the sphere here has radius big R, and 1 over 4 pi epsilon naught evaluate my potential over the surface of the sphere. So this is how you do your averaging procedure. Let me leave that out for right now. So we've got our average of our potential evaluated over the surface of the sphere and divided by the surface area of the sphere gives me the average value of my potential. So I'm going to plug in what V is here. And in this case, it's convenient, I think, or more useful to write the separation vector as our cursive rather than writing it out. So our cursive here is equal to square root of z squared minus 2zr cosine theta plus r squared. So in other words, it's the distance from this point Q to some point on the sphere, okay? And we have symmetry about the z-axis. So when we integrate over phi, that's just going to give us 2 pi. This interval becomes 1 over 4 pi r squared, qr squared over 4 pi epsilon naught times the integral of sine theta d theta d phi, all over square root of z squared minus 2z on cosine theta plus r squared. You really should be careful and put 2 integral signs there. Remember, we're integrating, when we integrate over phi, we're going from 0 to 2 pi. When we integrate over pi, or theta, we go from 0 to pi. Okey-dokey. 2 pi is going to get rid of half of the 4 pi. I'm going to change variables. I'm going to set u equal to cosine theta. And therefore du becomes minus sine theta d theta. We wind up with a minus sign here so we can flip the limits of our integral. And this becomes du over the square root of z squared minus 2zru plus u squared. And we'll be left with a factor of 1 over half minus 2zr, and I'm going to integrate this minus 1 to pi, minus 1 to 1, and Usually when I take the square root of these kinds of quantities, I have to be careful and take the absolute value. However, we're evaluating this for z greater than r, so I don't need to worry about my absolute value sign because I've already taken that into account. When I add these two up, the z's cancel out, and I'll be left with minus 2r in the numerator. Giving me q over 4 pi epsilon naught z. And remember again, we evaluated this on the z-axis just to make our lives a little bit easier. So I can generalize this to any direction r. That gives me q over 4 pi epsilon naught r. But that's just the potential due to this point charge. So basically, the potential at some point r, which we've taken to be the origin here, is equal to the potential averaged over the sphere centered at that point. So that's a very important result, and that tells us that all of our maxima have to occur on the boundaries of the problem. You can't occur in the middle. You can't have hills and valleys in the region in which you're solving. Okay. So now we've talked about averaging procedures. Let's talk about uniqueness, and this will give us justification for solving Laplace's equation. Okay, so let's say we've got some region of space, and I'm going to enclose it by some surface S. So S represents either a real physical surface or surface at infinity. And we'll call this region inside volume V9. Okay, I'm going to assume that I've got conductors inside of here. Use Roman numerals to distinguish one surface from the other. So we've got S1, S2, all the way up to Sn. I'm going to assume that I know what the solution is on each of these surfaces. So either I know the solution itself, or I know the partial derivative with respect to n. So we're either given V or a partial derivative of V with respect to n on each of the boundaries. So you know the potential, or maybe you know the charge density. Okay? I'm going to assume that I have two solutions. two solutions of Laplace's equation. I'll call them V1 and V2. V1 and V2, assume at first, well, maybe they have different values in here, maybe they don't, but they do have the same value on each of the surfaces. So in other words, if I'm given the potential on this surface, that would be VI, or V Roman numeral 1. Over here, this would be V Roman numeral 2, or you might know what the derivative is. So V1 is a solution, and V2 is a solution. I'm going to assume that, or take the difference between these two. And call it V with little bars on top, or victory sign here. And that's equal to V1 minus V2. Well, it follows immediately that if V1 and V2 are solutions, our V for victory also has to be a solution as well. Okay, V1. We assume two solutions, V1 and V2, and take the difference between those two. That difference also has to be a solution as well. Now I'm going to look at an integral here. I'm going to evaluate the divergence of this product and evaluate the integral over this volume of space. Okay? Using the divergence theorem, I can convert this over to a surface integral. And all the surfaces we have to take into account, we don't just take into account this surface as the boundary region, but all the surfaces of the conductor. So in other words, this integral is equal to this surface integral over the surfaces of all the conductors plus the bounding surface, which, as I mentioned before, can either be a real physical surface or a surface at infinity. This becomes this V for victory here, gradient V dot n dA. Now, this has to be 0. Why? Think about this for a minute. We've said that we know what our either the potential is on the surface, or we know what its gradient is on the surface in the normal direction. So, if we know what the solution is, and we're saying that phi is equal to V1 minus V2, basically we're just saying that this or this has to be 0 on every surface. So therefore the integral has to vanish. Okay. Now I'm going to make use of that vector identity to write this out in two terms. So just as a reminder, for any product of any scalar and a vector, take the divergence, that is the same thing as taking the dot product of the vector and gradient of the scalar plus the scalar times the divergence of the vector. You rewrite this volume integral as this term is going to give me the dot product of gradient of V for victory and the dot product of the gradient of V for victory as well. The second term will give me 3 times the divergence of the gradient of v for victory. This first term is just going to be the square of the gradient of for victory. Second term we have the product of our potential v for victory times the Laplacian. Well, I know this term vanishes. Why? Because I know this v is a solution of Laplace's equation. The second term vanishes. So this left-hand side has to be equal to this right-hand side, which we figured out was equal to 0. And I'm left with this integral. Integral over something that's intrinsically positive is equal to 0. So this term here, this integrand, either has to be positive or it's 0. And there are two ways about it. We're only talking about real functions here. So the only way this integral can vanish if this is positive, 0, is for this to be 0. So therefore, that gradient is equal to 0. And that tells me v has to be equal to a constant. If we are told what the potentials are, in other words, if we're just given the v's over each of these surfaces, we know this is a constant value. Well, then it's going to be constant throughout the whole region of space. So therefore, because that's equal to 0 on all the boundaries, this has to be 0 if we're given v's on the boundaries. If we happen to be given the normal component, another way of writing that is gradient of v dotted into the normal. That tells me that at most v has to be some constant value. So therefore, what's the upshot on all this? Well, if v is equal to 0 everywhere, that tells me that v1 and v2 are the same function. In the event that we're given the normal, at most v1 and v2 differ by a constant value, and constant values are basically you've got your solution. Okay? So we've established now that if you find a solution to Laplace's equation, you are guaranteed that you found the only solution to Laplace's equation. So what that means is that if I come up with a problem and I take a wild and crazy guess, and that wild and crazy guess happens to satisfy Laplace's equation, it happens to satisfy the boundary conditions, I'm guaranteed that I have the right solution. Of course, taking wild and crazy guesses is usually not the best technique for solving electrostatic boundary problems, but it actually is a valid method. We're going to be getting into some more methodical techniques for solving these problems in the next lecture. That concludes today's talk, and next time around we'll be talking about the method of images.